So let's do a little experiment. I have 8 coins represented here by 8 circles. And what I'm going to do is take these coins, throw them into a cup, and toss them. I'm going to pull all the heads out, count the number of heads, put those back in the cup, shake them, and toss them out again. Keep doing that. Now, if I were to do this with coins in real life, I would obviously not get the same number of heads every time, right? Because there's an element of chance to this. But if things were to follow probabilities perfectly, then I would get the same number of coins every time. So if I were to make a little t-chart over here saying for the number of tosses and the number of heads, I started with 8 coins. After one toss, if probabilities were perfect, half of those, which is 4, would be heads, right? Now, if I were then to toss out those 4 tails and toss these heads again, I would expect half of those to end up being heads. So these might be tails, it would go away. And I would have 2 coins here, right? Now the 2 came from taking half of this 4, which is half of this, right? So that's half of 8 times a half. If I were to toss it again, this one might be a tail, be down to 1, which is the 2 times another half. Now you can see we're sort of building a pattern here as we go through this number of tosses, right? So we started with 8, then we multiply 8 by half, and then we multiply 8 by a half twice. So it's 8 times 0.5 squared. And then we multiply 8 times a half 3 times. So if I kept going and probabilities were perfect, this coin would rip itself apart and half of it would come up tails and half of it would say heads, right? So we would have half a coin, which is basically the same thing as 8 times 0.5 to the 4th. Now, if I were to keep going here, you see there's a pattern in the number of coins that I have left over here. It's 8 times a half to a power, and that power is the number of toss we're on. This is a type of function called an exponential function. So if I were to try to go down to, say, the xth toss, my pattern in this situation would be 8 times 0.5 to the x. And an exponential function is a function in which a variable is in the exponent. And that's what we're going to be starting with in this chapter. Now it'll do us good to look at this expression that we just found and recognize where everything came from. So the 8 here came from the initial number of coins I had. The half here, the 0.5, is the percentage of things I had left after each toss, right? This was something that decreased at a constant percentage. It went down by 50% every single time. That's what causes an exponential function, is when something's decreasing by the same percentage every single time, or increasing by the same percentage. And then this was the number of times that we actually decreased the thing. Now, what we're going to do is look at some different situations that are also exponential, but in all of these, you're going to recognize that these are all constant percentage changes, either of increase or decrease. So, let's look at this first one. Population of 100 rabbits is known to grow at a constant rate of 5% per year. How many rabbits will there be? So what we're going to do here is we're going to start with that T-chart idea that we did before. My X is going to be the number of years, and my Y is going to be the number of rabbits. So when we start, we have 100 rabbits, right? Now, after 1 year, the number of rabbits increases by 5%. Now there's 2 ways of thinking about this. You can multiply 100 by 0.05 and then add that to 100, but there's a little bit of an easier way of doing it. If I have 100% and I'm increasing it by 5%, that means the amount I'm going to have left is going to be 105%, right? If you write that as a decimal, that's 1.05, and that's what you can multiply the 100 by to get the increase of 5% added on. Which means basically, if I wanted to figure out what was going on after 3 years, after 2, I'd multiply this number by another 1.05. And after 3 years, I'd multiply this number by another 1.05. And I get 115.7625. Now listen, there's not going to be 0.762 of a rabbit jumping around. So when you're answering a problem like this, where the thing has to be like a whole number, you can either say, hey, there's no such thing as, 0.762 of a rabbit. So I can say there are 115 rabbits after 3 years. That would be what's called truncating. It's basically just chopping off the decimal. Or I could say the 0.7625 rounds up. Either of these answers would be acceptable, but don't leave it as don't leave the decimal there because we don't have decimal parts of a rabbit. Now, if I were to look at these patterns, you see, again, we have the initial population, the percentage of growth, basically, added to 100%, and then this power is the number of times it's been done. So if I wanted to do 10 years, I'm not going to go through and do 10 lines of this. I'm going to recognize the pattern and say, after 10 years, this would be my population. And as I punch in my calculator, that would be 162.889. So you could say 162 or 163. And the same thing for 20. So I would basically type in 100 times 1.05 to the 20th. That gives me 265.329, which would round down and truncate to 265 rabbits. So the relationship here was that the number of rabbits was the initial number of rabbits, 100, times 1.05, that's the percentage growth added to the 100%, changed to a decimal, to the x. Now, similar problem. Value of a car declines at a constant rate. So what I'd like you to do is pause the video and see if you can come up with the relationship in this problem. Okay, so what we're going to do now is we're going to look at this and say, we're going to, same sort of reasoning we did up here. The initial amount is 24,000. So I could make my t-chart or I could jump straight into the equation. I'm going to do the t-chart just for a couple of lines this time. So my x is going to be the number of years, and my y is going to be dollars. So I start at 24,000, and then after 1 year, my car's going to decline at a constant rate of 3.2%. So again, the way I want to think about it is it's 100%. This time it's declining, so it's shrinking, minus 3.2%. That would give me 96.8%. And then if I change that to a decimal, 0.968, that gives me the number to multiply 24,000 by to get to the next value. So after 2 years, I'd multiply that by the same number again. And so the relationship I end up getting is the initial amount times 0.968 to the x. And then I could plug in 5, 10, and 20 into that relationship instead of having to go through and do all this multiplication and t-chart stuff. And these are the values that we get. Now, these two problems are types of exponential functions called exponential growth and exponential decay. So when we think about the coin problem, remember we started with 8 coins, and then we went to 4, and then we went to 2, and then we went to 1, and then we went to 1/2, and then it would be like 1/4. And so you see how it kind of like starts dropping off steeply and then leveling off as we go along? That's an example of exponential decay. Exponential decay is when a value or population is decreasing by a constant percentage. Now in the coins it was 50%, and the car declining it was 3.2%, but the percentage being the same is what made it exponential decay, so it kind of looks like this. Exponential growth is when the value is increasing by a constant rate or constant percentage. And instead of starting off by dropping quickly and then leveling off, it's going to start with a level and start growing more and more quickly like that. Now, both of these graphs have asymptotes. They basically have an asymptote at 0 because you can tell the graph is like leveling off and getting closer and closer to 0 as you go along. Now, anything that grows or shrinks at a constant percentage rate, as the things we've done above, can be modeled by this formula. So the formula is y equals the initial amount. So let's say y is the final amount. The initial amount, which is the starting amount, let's call that P. And then let's call our rate of decay or growth, that's our percentage changed to a decimal. Let's call that R. Now remember, inside the parentheses, we either added the percentage to 100% or took it away from 100%, depending on whether we were growing or decaying. And 100% as a decimal is 1. So you'll see if you write this thing as a decimal, the thing inside is going to be 1, that's the 100%, plus or minus, whether it's growth or decay, not both, one or the other, right? And then the R as a decimal. And then at the power, this X, is going to be the number of times the growth occurs. Now, let's look at some examples on the next page. Now, I'm going to rewrite my formula that we just came up with at the top of the screen. And an X there. Now, one of the things that you need to know, this 1 plus R is all about doing the 100% plus or minus the rate of decay or growth. If you would prefer to think of it as doing 100% plus or minus the percent, and then change that to a decimal, you can do that instead. And that's what I'm going to do on this problem. So if you read this problem, we're going to be talking about money, a decent amount in this chapter. And so one of the things you'll talk about is interest. And interest, of course, is money that you earn when you invest money somewhere. So an annual percentage rate is basically how much money you would get if you left the money in the account for a year, what you would get at the end of the year. Now we're going to use the same formula. So what I'm going to do here is say I'm gaining 2.7%. So my 100 plus 2.7% is 102.7%. But I need to change that to a decimal before I put it in the formula. So when I go to use my formula, it's going to be y equals my initial amount, 10,000, times that percentage as a decimal, so 1.027. And again, that's 1 plus 0.027 if you'd rather think of it that way, to the x power, and x is the number of times that it's being calculated, that's growing. So it's growing yearly, it's 20 years, so that's going to be a 20. So when I put that in my calculator, I get 17,037 and 62 cents. And of course, since we're dealing with money, now it makes sense to include decimals, the hundreds. So you really should sort of look at the context of the problem to figure out what you should include, right? How far you should round. All right, this last example is the last one we're going to do on this video. So this is harder because there's some information that's missing here. So we, in order to use this formula, and again, I'll write it up here. Now this is decrease, so I'm going to go ahead and just write 1 minus r there. We need the following variables. Get that as an r, good to keep it in the same order. Now, population in Cleveland in 2010 was 398,815. So let's make that our initial, because that's the earliest time we see in the problem. We're told a population that it had shrunk to in 2020, right? And then we're told that assume this decrease continues at a constant percentage rate, which tells us we need to use this formula, because that's what makes it exponential. What would the population be in 2100? All right, so we're missing some information here. We don't know a rate, first of all. However, we do know how much the population declined from 2010 to 2020. So if I were to take the population in 2020 and divide it by the population in 2010, that would give me the percentage of the population that was remaining in 2010, right? So it's sort of like taking the 100 and like subtracting away the percentage of people that left. It's just a shorter way of doing it. Now in this case, you get 0.95535, et cetera, et cetera. So that means we had 95.5% of the people. I would probably go ahead and throw a couple more decimal places in there because it makes me happier to do so. So that means this thing here, this is not just the rate, because that would be the rate of decrease, right? This is what's remaining. This is the 1 minus that R. So 1 minus R then is 0.95535. We're looking for a final amount, and then we need to know how many times the growth has occurred. So my initial population is in 2010, right? And my final population, I want it to be in 2100. Now that's 90 years. However, this percent growth happened in a decade. So in 90 years, there's only going to be 9 of those decades that pass, right? So instead of X being 90, meaning this population decrease happened 90 times, it's going to happen once per decade. So it's going to happen 9 times. So now if I take everything and plug it in, and then pop that into my calculator, I'm going to get 259,811 and some change, but these are people, right? So we can round this to a whole number. And there's my population in Cleveland in 2100. Now we will talk more about exponential functions in class next time.